Record to cloud. We're good.
All right. Thank you very much for that introduction, Mark. Thank you all for joining us. I'm Ajit Naik with Baumann Consulting. I'll be presenting today's talk on Introduction to Geothermal Exchange Systems with a focus on urban environments. So as you guys, as I go along for this, I'll periodically stop for questions, but I really encourage all of you, if you've got a question, to drop it in the chat so Mark can read it out, or you can just go ahead and come off mute and ask me a question if there's something burning that pops up or piques your interest. Hopefully I've timed this presentation to take about an hour, and we'll have some time at the end for additional questions. I believe we have up to 90 minutes, but I hope to keep you only for about an hour today. So really, today's learning objectives are fivefold. To understand the basics of what a geothermal heat pump is and how geothermal systems work, to learn what a hybrid geothermal system is and how they enable greater use of geothermal in urban settings, learn about innovative heat sink and heat source options that work with heat pumps in urban settings, learn about the state of the art with respect to installing geothermal ground loops beneath existing buildings, which is a big topic in urban settings, especially in DC, and to understand the basics of financial incentives that are pretty unique to geothermal heating and cooling systems, how to pay for all this stuff. So hopefully sticking with us today, you'll be able to, discuss on these subjects. So basically, why urban geothermal heating and cooling systems? So really, there's a twofold goals in DC and in sustainability writ large around the U.S., North America, and really the world. The first, as we all know, is reducing energy use. There's a mandate for us to draw down our energy use, have more energy efficiency, ultimately to minimize impact on the environment. And secondly, what we're seeing definitely in DC and also starting elsewhere is a ban on site fossil fuel use on site. So that is no combusting things on site, no burning gas, no burning wood, no burning coal. The idea ultimately is to stop burning things entirely, both to generate electricity as well as on site in our buildings to meet our needs. So geothermal heating and cooling systems are a great way of, both driving down our energy use. They're really efficient at providing heating and cooling, and they also don't have any fuel combustion on site. So that's really the big draw of these systems, is they're the most efficient possible systems that can meet our needs without burning anything to do so. So they make them very attractive. Forgive me, I'm an engineer. I love diagrams, so you'll have to stick with me today. I want to give a little bit of a background on what a heat pump is. So a heat pump basically is a device or a system that pumps thermal energy or heat from a low temperature source to a high temperature source. You might be familiar with one of these devices. You have one in your home right now. It's called your refrigerator, right? Which pumps heat from the inside of your refrigerator, which is cold, to the outside, your room, which is relatively warm. So your air conditioner does the same thing. You might have a window unit or, a condenser in your backyard. But when it's blowing cold air on the inside, it's blowing warm air on the outside. It's, laws of physics. So in the same way, a heat pump is a device that's meant to be reversible, and that also can move heat in either direction. So you've got this diagram right here, which shows something similar to what you might have in your house, an air handler on the inside and a condenser or, something outside. So what we have is a compressor that circulates high pressure, hot refrigerant to the inside where, your fan blows it off and blows warm air to the inside. This refrigerant cools down, goes through an expansion device, which cools it down even further. It's kind of the same way if you've ever held a can of duster or a can of hairspray upside down and noted that when that high pressure liquid comes out into the world, it cools off. It's the same effect. And this cold refrigerant is very, very, very cold, right? Much colder than it is outside, even in the winter, right? This refrigerant might be minus 15, minus 20, minus 30 degrees Fahrenheit. So it's actually able to pick up heat from the outside and repeat the cycle. So basically, this device is more or less like an air conditioner, right? That just can be run in reverse. So even when it's cold outside, it can extract heat from the air and then together with the electricity, deliver it to the inside. So a few caveats on that, right? So a heat pump's capacity and its efficiency are really dependent on the temperature of the source, right? So let's say, we're trying to warm up the inside for whatever reason, and it's 95 degrees outside. It's July, right? It's super warm out. This device is going to have a real easy time getting heat from the outside. It's going to only need just a little bit of electricity to do it, meaning it's operating really, really efficiently. However, let's say in like February, January, when it's real cold out, maybe let's say we have a cold 15, 20-degree day, it's not really that warm outside. The temperature difference between the refrigerant and the air is not as much, and it's not able to pick up as much heat. So the compressor has to work a lot harder to meet the heat demand inside. It's a lot less efficient. So basically, this device can either extract heat from the outside or it can reject heat to the outside. But fundamentally, it allows, using refrigerant, the transport of heat from one place to another. So a little word on heat pump efficiency. So, we, as mentioned, that device really just takes electricity, right, from the grid. You plug it in. So let's say you buy for a given hour, about 1 kilowatt hour of energy from the grid to operate the system. Typically, these devices are able to absorb, depending on how warm it is outside, 2 to 3 kilowatt hours of energy from the outside air. And, again, first law of thermodynamics, all this heat gets added together and goes into the building, which yields 3 to 4 kilowatt hours of energy as heat usefully to the building. So that means these systems are 250 to 300% efficient, right? Because in terms of we just put in 1 kilowatt hour in, but we got, 3 to 4 kilowatt hours out. However, as mentioned, not only the efficiency drops with temperature, but also the capacity. So what we're looking at here is a 3-ton air source heat pump and its performance versus OAT, which is outside air temperature. So we can see, the efficiency is this red line, and the capacity, I mean, how much heat it physically can put out, is the blue line. So, on a cool but not too bad day, say in the low 50s, we have an operating efficiency of 3.3, 3.4. That means for every 1 unit of electricity we put in, we're getting 3.3, 3.4 units of heat out. Pretty good. At the same time, we get a capacity of almost 37 kilobTUs per hour, right? That's pretty good. But as the temperature starts to drop off, and as we approach those really cold days that we get in January, February, about 15 degrees is the heating design in DC, we lose quite a bit of our capacity. We're down to about 27, right? That's no joke. We lose about a third of our capacity when it gets really cold outside for this unit. And same thing on the efficiency wise, not only do we lose our, how much heat we can put out, we're generating it much less efficiently, right? We only get 1.5 units of heat for every unit of electricity we put in. So these air source heat pumps, which is the most common heat pump that you'll see, or when you go to Costco or Home Depot and the person at the exit tries to get you to buy a heat pump unit, this is usually what you're seeing. The technology has really improved a lot, right? So over the years, the low end temperature used to be 30, 40 degrees. Now you can get these units working down to, -5, -10, and even colder than that. But ultimately, it's something to keep in mind, right? That when you're using air source heat pumps, that the efficiency and the capacity drops. Just for reference, burning 1 unit of gas in DC and using 1 unit of electricity, the same unit of electricity in DC, it emits about 2.5 times the carbon dioxide equivalent using the electricity as it does to just burn gas on site. Right. So that's all in well up here, when it's not too cool out with this unit, we're 3.5 times, we're getting 3.5 units of heat to every 1 unit of electricity. Gas, on the other hand, is only 80, 90% efficient, 0.8, 0.9. So when it's real warm out, or kind of cool out, we're pretty good. We're definitely emitting less carbon dioxide equivalent than we would if we were burning gas. As it starts to get colder, however, colder and colder and colder, the efficiency drops. Once we get below about that 2.5, 2 times number there, all of a sudden, using a heat pump down here when it's real cold outside is actually less, it emits more carbon than you would if you were just burning gas in a gas furnace. So it's really important to consider, the range of temperatures that you're going to use these devices over. Once the grid gets cleaner, some years in the future, they switch to more renewable energy with time, and we do see those changes. This story might change. But for buildings that get built now, retrofitted now for operation in the next 10, 15 years, you know, these are real considerations that have to be taken. So again, just a couple summaries of those numbers here. You know, our efficiency is reduced 22% at 17 Fahrenheit. Our capacity is reduced 28% at 17 Fahrenheit. And the kind of that crossover point where it becomes kind of less damaging on the environment to actually use gas than it would an air source heat pump is also indicated as well. This brings up other technologies. You know, do we have to take the heat from the air? So this led folks to come up with the idea of water source heat pumps, right? You can see on the right, you have a bunch of little heat pumps, right? Like say, for example, in hotel rooms or in apartments in a multifamily building. And all of those heat pumps, instead of extracting their heat or cooling energy from the outside air, they're piped, right? They get a stream of neutral temperature water, nice, right around 50 degrees, can act perfectly as a heat sink or a heat source all year round, right? So maybe some of these units are extracting heat, maybe some of these units are rejecting heat and cooling, and they can all share that energy and kind of have this common loop of always neutral temperature energy. They're really beneficial because you can exchange energy. You know, if half of your units are calling for cooling, half of your units are calling for heating, you know, you've got kind of got a balanced load, and this system can actually be used to share the heat among different units. You know, in the middle of the winter, though, when it's real cold outside, all of these guys are going to be drawing heat out of that common water loop. So we need a boiler or some kind of heat addition, you know, to kind of provide that heat at the low end. Historically, this has been a gas boiler, but it doesn't have to be, and we're coming to that. Same thing in the summer when all of these units are in cooling, you know, the water is going to start getting hotter and hotter and hotter as these units reject heat to it. So we need a cooling tower, you know, blow some air off of it, cool that water back down and get it to within the range that the heat pumps can use it. So these systems usually have an operating range of like 40 degrees Fahrenheit up to about 90 degrees Fahrenheit, much more constrained, right, than what you see outside when in DC, which Lord knows we get those 110-degree days in the summer and we get those 15-degree days in the winter. So, you know, a water source heat pump allows the heat pumps to operate much more efficiently, right, because it maintains their temperatures, but we have this cooling tower, we have this boiler. These things also use energy, right? So they chew into a lot of the efficiency gains. While there are some efficiency gains to sharing the load, you know, the cooling tower and boiler really eat away at a lot of those. And the boiler, for the most part, is gas, which doesn't do a lot for us. You know, our goal is to electrify and stop burning things in our buildings to meet our needs. So this led to the idea of how else could we provide, you know, that heating and cooling instead of a boiler and a cooling tower. That's the idea of a geothermal heat pump. So the key point is basically, you know, in the wintertime, when all of our heat pumps are kicking out cold water because they're blowing warm air, we need a way to warm that water up. If it's not cool to use a boiler to warm that water up, the idea behind geothermal is to use the ground. You bury pipes in the ground where it's always pretty steady, you know, kind of neutral temperature. It never kind of down below the frost line. And in the winter, you know, you can extract that energy right from the ground. In the summer, you can reject that energy right back to the ground. Even like a little squirrel, you can store the heat that you reject in the summer underground for your use during the winter. This makes it super efficient, right? So you aren't using a boiler, you aren't using a cooling tower, you've got a heat pump, but instead of exchanging with the air, which gets really cold in the winter, you're exchanging with the ground, which is kind of nice and, you know, comfortable all year round, both warmed by the heat from the ground below, as well as by the sun, you know, hitting the ground above. So the thermal energy, you know, does move pretty slowly through these geologic formations underground too. So when you put that heat underground in the summer, like I said, it stays there. You know, it'll dissipate a little bit, but for the most part, if you know, you warm the ground up to 90 degrees by the end of the summer, by the start of the winter, it's still going to be pretty warm, right? It's going to be still 70, 80, 85 degrees. It's not going to be the 50, 60 degrees that it would be if you hadn't been storing heat down there. So basically, a geothermal heat pump is a heat pump connected to a giant thermal battery, which is the ground. So as I said, it works in both directions, not just in heating, in cooling, but in heating. Both times it can reject it or absorb it. So these units are a lot more efficient. Since, as we discussed, these units efficiencies are really tied into the temperatures, and when it gets really, really hot outside, consume a lot of electricity to cool. And when it's really, really cold outside, they consume a lot of energy to heat. But ground source heat pumps, which are connected to the ground, never really get that cold in the winter, and they never really get that hot in the summer because they're connected to the ground, that thermal battery. So when we put in our 1 kilowatt hour of electricity from the grid to operate it, we end up getting more. Instead of just 2 or 3 kilowatt hours of energy absorbed from the air, we get 3 or 5 kilowatt hours of energy absorbed from the earth. This ends up with 4 to 6 kilowatt hours of energy totally as heat into the building. So these are like 400 to 600% efficient. So whereas those air source heat pumps are like really only 2 to 300% efficient, a coefficient of performance of 2 to 3, geothermal heat pumps are often twice as efficient just because, they're working with that thermal battery in the ground. So before I continue about explaining kind of the nuts and bolts of how the systems work, any questions from folks on the line about our broader concepts of geothermal systems? Okay. All right. So as an aside, before I get into it, lots of times you'll hear different terminology here, right? Like the most common, I think, is geothermal systems. Sometimes that makes people think of like deep ground systems, like, in Iceland or somewhere where there's volcanic energy and you're boring way down into the earth. So while that's the industry kind of term for it, this is really not about that, right? These are much more shallow, storing energy in the ground, not really tapping in primarily to that kind of deep ground energy in the same way. So these are, by the engineers and eggheads working in the industry, typically called geo exchange systems or ground source systems, which are a lot more of a mouthful than geothermal. So often we end up just seeing them called geothermal systems. So whatever you want to call them, ground source, geothermal, geo exchange. There's basically three main components. There's the ground heat exchanger, right? Like this is the part that's buried underground that water flows through and either heats up or cools down the ground. There's a few main types, which we'll discuss. There's closed loop, open loop, and it's kind of an oddball surface water loops. But no matter what, there's some kind of device, right? And you can see some pictures of them there, that's buried underground or in a body of water that allows the heat pump to basically draw energy from and reject energy to. There is the heat pump itself, right? Like you see a few pictures of them here. They kind of look like boilers in some configurations. Sometimes they look like air conditioning units. You really can't tell the difference. But either way, they are an air conditioner or a kind of a chiller looking device that has connections for condenser water or source water that comes from the ground. And lastly, you have a distribution system. The heat pump either generates hot water in the winter or cold water in the summer, or air in the winter or cold air in the summer. So it doesn't matter. You can have, an air system like a furnace, like you probably have in your house that, blows air. Or for those of you that work in the commercial space, you might have hot and chilled water distribution, like a radiant floor or fan coils or something similar. So regardless of the application, right? Like whether it's a single family home, putting in a home residential scale geothermal system, or this is like a massive university campus, putting in like a giant geothermal system to serve the entire campus, these components remain the same. There's always a heat exchanger buried underneath the ground. There's always like a refrigerant-based heat pump that takes that water and either uses it to generate, hot air or hot water, or cold air or cold water. There's some kind of distribution system, right? Like a typical air handler or pumps that distribute that heating air or heating water or cooling air or cooling water throughout the space. So I want to talk a little bit about that first component, the ground heat exchanger. So the first and kind of oldest type are open loop systems, right? So this open loop system, really the thing that makes it an open loop is it relies on underground aquifers, right? Like kind of natural groundwater sources that always is at a neutral temperature that from down below the pumped water level. So you kind of tap into these aquifers, you pull in the heat or take out the heat from it as you seasonally need, and then you take the water that's now warmed up a little bit or cooled down a little bit by your activities, and you put it right back down into the ground. So this is really favorable for a few reasons. It's super efficient, right? Like that water that comes from deep, deep underground is always the same temperature. So there's actually very little variation at all. It's like always 50 degrees, which is like perfect for heat pumps right at the top of the system. Obviously, it's really only limited to where you have suitable amount of groundwater. There are places, Florida, other places where this is really feasible, but it's not feasible if you don't have the proper hydrogeologic conditions, right? If there's not a lot of groundwater, you're somewhere in the desert, and it's not really easy to get the water back down underground, right? In Florida, the water table is really high, so you can just put it right into a well. Other places where the water is a little bit down deeper, if you just discharge it at the surface, it might not make it underground the same way. So sometimes it has to be put back underground. You got to be real careful with water chemistry, right? You got that the water chemistry can change. It can corrode your pipes. It can corrode your materials. It can lower the span of your heat pump. Those of you who have worked with cooling towers know that water chemistry is really important there. That's usually for health and safety reasons, but it's not any different. Ultimately at the end, you need to make sure that your chemistry is balanced to avoid adverse outcomes. And here, those can impact your building and its longevity and also environmental impact. We don't want to be returning, dirty crud back into Mother Nature. So, just to kind of mention that these are out there, they exist, they're common in some parts of the country, but this isn't really a thing in DC or really the DMV even more broadly. There's another kind of open loop system called a standing column well, right? So this yields like 10 to 30 tons per well. It's the second most efficient, right? So St. Patrick's Cathedral in Manhattan uses this type of system where it basically is like a sealed well, goes down, pumps up the water from under the ground and uses it in the same way. So it doesn't rely on an aquifer. Its pumps can be done in a little bit tighter formats, but it really works well. You've got rock, right? If you've got soft, salty, sandy, clayey, like smushy stuff down there, this is really not good. You get a lot of crud in it. It's difficult to operate. But if you're built on bedrock and you've got groundwater that's at a reasonable source, it's something that's feasible. So this does work well in some places in the DC area, in the DMV. So anywhere that lies west of I-95, it's possible. And the reason that that's possible is so I-95 actually follows the fall line, which is the transition from the coastal plain to like Piedmont, like the Piedmont geology. So cities have actually mostly developed along I-95 because that's kind of where that was like the end of like the navigable riverways. Like people couldn't get any further than that. So hey, might as well stop here and build our cities. So it also is kind of the point where you go from deep overburden, that's like soil and like the soft stuff, to hitting rock kind of at shallow depths. So for like all of these reasons, kind of looking at your project, if it's west of 95, an open loop system is something that could theoretically be possible. Again, closed loop systems, which we're about to get to, are more common, but this is a thing in the DMV that might be possible for projects that you're working on. The same caveats apply. You have to pay real close chemistry to your attention to your water chemistry. You're still pulling in, groundwater that might have changing chemistry, specific high pH, low pH, and you have to make sure that you account for that, both for the longevity of your equipment as well as for the discharge back to Mother Nature. There are other places too. Sometimes permitting can be an issue. In Northwest DC, you could do this, but given the local geology, but can't permit this type of system there. So just because it sounds like a good idea doesn't mean you won't run afoul of the regulators. And in general, open loop systems are much more scrutinized and subject to that type of regulation. So that brings us to closed loop systems. So closed loop systems, as you can guess, don't draw water from nature, don't discharge water from nature. They have a fixed amount of water in them to begin with, and that water circulates throughout the cycle and it never leaves, our systems. That means it never goes into nature, it never comes out of nature. So that means we got to put this pipe somewhere, right? We got a big, huge, long length of pipe that we're going to run water through, and it's got to heat up or cool down and exchange with the ground. So one of the most common types that you see isn't even the ground at all, but a surface water loop. This is more commonly called a pond loop, right? Like I'm originally from the Midwest, and these are pretty common out there. And it needs a little bit at least 4 feet of water. The more you have, the better, because the warmer it's going to be at the bottom. But fun fact, generally the water at the bottom of ponds doesn't freeze, right? Like even when it gets like super cold outside, if it's deep enough, the bottom of the water generally settles out around 39 degrees Fahrenheit, right? That's because, the water is the most dense at that point, and it typically kind of stays that way and starts to freeze from down, but you don't, even in very, very cold climates, get anything colder than that. You'll note that 39 degrees is quite a bit colder than the aquifer temperatures I mentioned of, 50, 55, 60 degrees. So, in cooling or in heating in the wintertime, pond loop systems aren't quite as efficient, right? Because we are trying to draw heat from a colder source. Laws of, first law of thermodynamics, it's colder outside, our source is colder. We need to put in more electricity to deliver the heat that we need. So we got a couple of pictures of them here. It isn't anything fancy. It's literally like coiled high density polyethylene piping that just goes out in big coils and sits at the bottom of the lake. Sometimes they put it on a matrix, like you can see, like chicken wire to kind of keep it spread apart and working, but it just anchors down on the bottom, you know, kind of sits there. These are also sometimes used in rivers too. Often the times you see a power plant next to a river is because it uses that water for cooling. So you see these again sometimes in next to rivers for the same reason. Again, we have an office in Chicago, and a lot of the big high rises right along the Chicago River use that as like a source for heating and cooling. Again, by the same principle that it's kind of down at the bottom. It never really freezes, and it's always warm enough to extract heat from. So the water generally it is warmed a little bit by heat from below, but largely it's the sun every day, even in the wintertime. Big body of water that's not totally clear is going to absorb a decent bit of energy. So really, the pond it's less stable than the air. Sorry, less stable than the ground, but it's more stable than the air because it does get some of that heat, absorbs a little bit more from the solar, and kind of offsets that loss of heat via radiation to the cold night sky. Another type of closed loop system looks very, very similar to the pond loop, except it's a horizontal loop. You just bury it under the ground, right? So you can see this takes up a lot of space, right? Like even for a smaller structure, it might take up like a whole football field of space. So, again, since these are not very deep, right? Typically you put them down below the frost line, but like you can see there, 7, 8, 10 feet deep. It's, not going super deep into the ground. So just like the pond, they're more susceptible to seasonal variations in temperature, right? So it's a bit less than the pond because it's ground, not water, but it works. It's cheaper to dig a big shallow pit than to go deep, deep underground. So that's why people do these. But these are really only a thing in like suburban settings or rural settings or like, industrial parks or places where you got a lot of room. So DC, like this isn't really possible. There's no projects that I've ever worked on, in the district that have space large enough to feasibly tolerate something like this. You get out into the exurbs, like maybe it's common in like residential applications, but for the most part, those of you working in the urban core area of the DMV, this is just something to know about, not something you'll actually work with. The one we're really here to talk about today is closed loop systems. Again, doesn't extract water from the ground, doesn't have anything to do with it. We pre-fill it with water and we circulate it, but it's a vertical loop. So instead, it's like imagine that horizontal loop, which was a bunch of coils and a shallow pit. Turn it 90 degrees and go down. So instead of going, 100 yards across, we're now going 100 yards down into the ground. So the vertical heat exchanger basically involves making a bunch of holes in the ground. Like some of you may have lawns and they get aerated. They put that thing over them and it pulls out the little things that look like goose turds, and there's a bunch of holes left in your lawn. It's basically the same idea, except very, very deep. You take a big drilling rig and you drill a bunch of holes in the ground. You stick the pipes down them with a U-bend. Again, they're connected to a heat pump. So in the winter, this water goes in, all your heat pumps extract heat from it, and the water gets real cold. It goes and circulates up and down, up and down, up and down, all these pipes, and it slowly picks up heat from under the ground. Sometimes they get warm deep enough to start tapping into the warmth from the earth. And, they warm up and you can keep the cycle going. In the summertime, Same thing in reverse, all those heat pumps blowing cold air, they're going to generate hot condenser water, which goes underground and it's stored in the mud, it's stored in the dirt, and it heats up the summer and it perfectly primes you for winter and you need to bring it all back out again. So it's like this beautiful cycle of like storing the energy like under the ground. These work a lot better than any of those horizontal distributions just because you're going down, right? Like you're less impacted by the sun. You're less impacted by the surface temperature. 100 feet down, 200 feet down, the temperature is like much more steady and much less impacted. If you penetrate through groundwater, sometimes you can take advantage of that, right? Like it's not quite as good as an open source, open loop system, but if you've got a closed loop in an aquifer and that's kind of washing your pipes all year round, hey, great. So these are really the money, right? For commercial and institutional and large scale applications and any type of urban application, right? Is gonna that incorporates geothermal, is gonna have some kind of vertical loop that goes down because it uses the least amount of surface area, right? It's just logic. Um, so I wanted to, for those of you who have not seen it before, I'm just going to share with you a video of what this looks like. I know sometimes Zoom doesn't do a great job of translating this, so hopefully it's not too grainy. Sorry, I took a vertical video when I did this. I don't know. My bad. But basically, these are common rigs that are used in the water drilling industry. Like that's who does it. Like if you were going to call somebody to drill like a artisan well, that's the same guy. It's the same rig that he brings out. A lot of them repivoted to geothermal. So basically, they drive up with this big old rig, and it has a bunch of pipes on it, right? Like you see, there's kind of like a whole, like basically quiver of pipes here, and one at a time, it rams one, drills it into the ground. It goes back out. It picks up another one, screws in, drills that one down, and it basically stacks the pipes one on top of each other, continuously drilling until you get down as deep as you need to go. It's a pipe, so all the dirt and everything that gets generated by the drilling activity gets sucked right out of the top. But basically, this is traditionally how drilling is done basically everywhere in the country. The circuits, for those of you who are engineers, are typically connected in a reverse return configuration. Without geeking out about that too much, that means the borehole that gets the water first, right? That the water comes right out of the heat pump and goes right underground. The water that comes out of that borehole has to travel like a long distance before it comes back to the heat pump. The same way, the borehole that's the farthest away from the heat pump, that the water has to travel the furthest before it goes in, that has a fast connection, like a really short connection to the heat pump. And you can kind of see an example of that right here, right? Where so the supply comes out, goes right down this well, but the return that comes out of that well has to go all the way around this loop before it goes back. And the point of doing that is it keeps it well balanced, right? So the same amount of heat goes into all of the wells, the same amount of heat comes out of all of the wells when you kind of do it like this. Okay, so a few notes on boreholes and construction. So now that we've seen like a video of that, they're big holes in the ground. You put the tubes down and you fill it up with grout, right? That grout can be bentonite, can be cementitious, really anything. These boreholes typically go about 250 to 600 feet in the DC region. That depends on geology and what makes sense in terms of drilling. You want to have to avoid changing your drilling methods. I showed you the most predominant one, but there are other methods. You don't necessarily use the same bit, so to speak, to drill in bedrock as you do to drill in soft silt. So, but typically 250 to 600 is about how deep you see in DC. As an aside, there are some startups and new companies out there that are trying to go a lot deeper with this, 800 to up to 1500, maybe even 2000 feet. There's a company called Bedrock Energy I saw doing that. They're actually using rigs from the oil and gas industry, like fracking rigs that go down, and they're repurposing them for, sustainable geothermal exchange systems, which I really love. Like that people who are designing drilling technologies for exploiting natural resources are now, repurposing those technologies for sustainable and environmentally friendly technologies. It's a really great story. But ultimately, no matter how deep they are, they're ultimately grouted. Once you put the tubes in, you grout them and surround them with cement or clay or something like that to protect the groundwater, right? Just so in case you do leak, And you've got propylene glycol or some kind of antifreeze in there that, it doesn't leach out and, infect the aquifer and get into the water supply. Um, Usually those grouts, like I mentioned, are thermally enhanced. They've got silica or carbon put into it so that it helps the heat get out in and out faster into the boreholes. Sometimes the groundwater in the area has low pH, like it's acidic, and that can degrade clay. It can like literally eat away at bentonite. So in those cases, you use like cementitious grout, like basically cement. Again, all of these choices are regulated market to market, municipality to municipality, but those are the common things that we see in DC. Yeah, a last note about U-bends, like the U-bend is at the end, is typically something that's applied. So using only factory installed single piece fittings, the less fittings you have, the less chances you have to break. And I think it goes without saying that, a huge piece of pipe, 600 feet into the ground, you know, encased in cement, that is something that you don't want the U-bend failing down at the bottom because it's going to be, it's going to be a pain to get that out or not, more likely not feasible. And you're going to have to abandon that borehole in place. So it's really, really critical, and we'll hit back on this, that you do what's necessary, not only to design these systems well, but install them in such a way, that they're, set yourself up for success. Don't be mindful of your failure points. There's some key parameters to check, just as I summarize, the grouting materials that are used, like is it acidic? Is it going to get eaten up? Mixing setup and procedures, you'll be shocked at the number of people don't read the instructions before. Sometimes it has to sit, sometimes it has to cure, sometimes it needs to be a little bit moisture. Who knows? There's all sorts of things that could impact it, but making sure that it's done right is really important. A Treme pipe, this is kind of a device that's used to continuously feed concrete in settings where there's already water. So in some cases, when you put in you drill the hole, the water, it'll get filled up with groundwater, and you need a way of displacing that water with the concrete. And the concrete needs to kind of flow continuously, so that can be a tricky aspect of it. And then making that the flow density at the top is right. Like as the grout goes down, it gets impacted by the stuff that's on top of it, and the density of the grout that you need to be putting in, like how liquid it is or how much aggregate there it is, that might need to change, like from what you put in at the deepest part of the bore all the way up to the top. So backfill, everything about it is really critically important. A note about HDPE piping. If you scratch the surface more than it's really strong, really resilient, lasts forever. But if you scratch the surface more than 10%, it's vulnerable to something called like slow crack propagation. Right. Once it's there, it's only a matter of time. It may not be today, it may not be tomorrow, but 5, 6, 7, 8 years from now, it's going to happen. So making sure this material selection is right, and also that your procedure and your process for preparing it and backfilling it is really all to protect your pipe, to make sure that you're not causing any leaks or causing any scratches that'll turn into leaks a few years down the road. Um, you know, uh, sorry, just a couple more images here. So now that we've talked about, the systems, like what they are, like how they work, what we typically find, in the DC urban settings, that is vertical systems, which are the most common and kind of will be the basis for the remainder of our conversation. So talked about open loop, we talked about pond, horizontal, but let's set those aside and focus on the deep vertical ground boreholes, which is more what you're going to commonly encounter in the DMV. So there's a really important design process that we have to follow. So, since these things act as a thermal battery, right? Like we talked about, you store heat under the ground in the winter, in the summer, and then pull it back out in the winter. It's not like designing a normal system. So those of you who are engineers and who have designed maybe, home air conditioning system or a home furnace, or even a more complex system like a boiler and a chiller, typically those are sized, just for the peak, right? Like on the coldest day of the year when everything is off and, we need some heat in here. Like how much do we need? Same thing in the summer when it's July and everything's packed to its gills and we got everything running and it's super hot out, what's our cooling load? So that's typically how you size HVAC equipment. But geothermal system, has this battery aspect to it, right? There's this thermal storage aspect to it. So it's not enough to know just what we're using at the worst case in the winter and the worst case in the summer. we have to have some kind of idea of how much heat it's using all year round and how much cooling it's or heat it's rejecting for cooling all year round. So we need not only our peak loads, but our off-peak loads and an annual profile for how much heat we're planning to suck out of the ground and how much heat we're planning to spit back into it over the year, like that sinusoid. Once we've got that, all under control, right, that helps us kind of inform not only how big of a heat pump we'll need, but how many bores we'll need, how deep they might need to be, how they'll be arrayed. Of course, some of those might be limited by design considerations. So it's kind of an optimization process where for your specific peak loads and your specific annual heating and cooling demand profiles, you kind of select preliminary operating temperatures, flow rates, you select your heat pumps, you kind of arrange them, kind of lay them out. This is like your first draft. Like, all right, based on what I know. How do you know about the ground parameters, like how deep it is, how wide they are? There's a lot of existing material that's out there, geotechnical surveys for projects that are already done, groundwater surveys. There's a lot of information where you can understand key ground parameters like the density of the rock, what kind of rock it is, the water content of that rock, the average temperature of that rock. So, a lot of that information is available to help you kind of do a preliminary guess. Definitely not good enough to finalize your design. Like you absolutely have to do a test bore at your site. Cross town geologic conditions can change dramatically. Hell, like even a couple blocks down the road, you might run into something totally different. So even if you have, a geothermal test bore at 500 feet, 10 blocks away and you're trying to do the same thing, you still have to do a bore, right? Like you can't design the system without doing the bore yourself, that test bore. Thankfully you can reuse that test bore in your system, but don't make the mistake of thinking that, hey, it's reasonably close by, or it's in the same city, or it's just one neighborhood over. Yeah, that's not enough certainty, right? You actually do have to go into the ground, conduct that site survey so that you can refine your parameters, right? Like I would never want to design a geothermal bore field with 500-foot wells, even if I took a bore of only 200 feet at my same location. Because I can't extrapolate what's happening between 2 and 500 feet under the ground with just a 200 feet bore, even if it's on my site, right? So your test bore has to not only be local to your site, but it has to go down deep enough to what you're planning on doing. And if you're not sure whether you need to go 300, 500, 600 feet deep, well, I guess you're going to be digging a 600-foot test bore in order to help decide and make that decision. So continuing on, and this is all, again, from the ASHRAE Handbook, Geothermal Design Process, the IGSHPA, IGSPA, not a great acronym, the International Geothermal Heat Pump Association. They also have a design manual where you can get all of this information. It's like a 500-page long thing, recently unified with the Canadian standards. So, all of this is laid out in gross detail there. So once you have it all kind of planned out, you determine and evaluate loop field arrangements, right? Like, how am I going to lay this out? Is it going to be a square, a rectangle, an L, a line? You determine the optimum ground heat exchanger dimensions, right? Like, let's say that you're heating dominated. Maybe it's beneficial to put them all kind of close together, so that that heat can collect in one place. Maybe you're cooling dominated. Maybe it's better to spread them out a little bit, right? So that heat has more space between the boreholes to dissipate. So it can change. There's sizing software, there's energy software that you can use to help kind of make these decisions. Of course, you might be limited by the property. In lots of times there's regulations to how close to the property line you can put these things. So, there'll be not only the optimum, but there will also be design restrictions that limit what you can do. You'll proceed on, figure out the depth, the bores, the fill materials, really all of those components, even how you lay out the pipes within it. All of those things impact how, what capacity you get. And slowly, starting from your first guess of maybe, hey, I need 50 wells and a 5x10 rectangle that are 400-foot deep, based on what your initial kind of raw desk review information is. By the end, you might end up with only 40 wells in a square configuration that are 100-foot deeper. And it's important to note that the wells are what drives the cost, right? Like these things are like $10,000 to $15,000 each. So you do the math. If you need 50 wells, it's 15K a well. That's quite a bit of money. So optimizing it to reduce your wells is always better, and it's typically cheaper to drill one deeper well than two shallower wells too. So there's lots of cost considerations that can affect this. Once you have all of the exterior side kind of laid out, you kind of move on to the interior, just like you would in any other building. Lay out interior piping, lay out your interior distribution systems, pick your efficiencies, optimize your interior air or water distribution, however it is. And you ultimately have a well-balanced, well-designed system that's going to meet your needs. So I've talked a lot about the battery, right? Like the storage aspect to this, about how geothermal systems are fundamentally different because they let you store the heat under the ground, like a squirrel storing nuts, and you can use it, for the winter. So this means that it's important, like that you have some kind of balance, right? So like if you're going to take a certain amount of heat out of the ground in the wintertime, you better be recharging it in some way. Otherwise, eventually, over time, you know, that temperature ground is going to freeze. Conversely, if you keep putting in more heat to the ground than you take out, it's going to boil at some point. So here, you're looking here at a typical building heating load, right? Like where we have almost no heating demand at all in the summer, but and we have a year-round cooling, right? So this could be like a school or maybe something with a data center in it or some kind of IT facility, anything. This facility has clearly more cooling annually than it does heating. So it rejects more heat than is extracted. So as you would expect, if you add more and don't take away as much, more heat in than what you take out, the ground is going to heat up. Eventually, this is showing here, typically you do a 20 or a 30-year simulation. Over here, by year 30, the maximum temperature coming out of this loop is starting to approach 100 degrees. A lot of these heat pumps have a maximum operating limit of 90, 95 degrees. So once you start getting 100, 110 degree water, forget about even well before you start boiling or any concern of that nature, you might just be like out of luck, right? Like the heat pump is just not going to provide any cooling if you're feeding it 110 degree water. So worst case, these systems can outright fail, or, even if it doesn't outright fail on the years leading up to it, it's going to get really inefficient, right? Because maybe it's still hot enough that you can work with, cool enough that you can work with it, but it's right at the limit of the heat pump. It's not going to operate very well. So it's super important that we consider thermal balance, right? That we design buildings that have reasonably balanced heating and cooling. That's all of, net zero buildings, passive buildings, really high efficiency, well-designed buildings typically are pretty thermally balanced, all right? But what about the rest of us, that are retrofitting buildings or can't afford a net zero building and are trying to do the right thing? There is a middle path, right? The middle way. It is a hybrid geothermal system. So in that previous example where we have more cooling than heating and there's no bones about it, we can design a ground source heat system, a vertical ground geothermal system, but then we have to add some supplemental cooling, right? Like, so for that time of the year when it's too hot, or, down the line when whenever the water temperature and those hottest months are getting a little bit, hotter than we like, we have this little backup fluid cooler, a cooling tower that just runs, just for those hours and kind of brings the temperature down. So for those of you who know the Pareto principle, sometimes you get 80% of the results for 20% of the effort. This is one of those cases, right? Where even if you design a geothermal system just to meet part of your load or for, part of your design, and you still have to have a little bit of supplemental heat rejection, like a dry cooler, or a little bit of supplemental heat addition, like maybe a little electric boiler or something, you work out. Usually you don't size these full, or like you're not providing like a full size fluid cooler or a full size, pony boiler. It's just big enough to kind of maintain the temperature, especially in DC. Other parts of the country, in the Midwest, they provide full size backups so that, you can still provide the conditioning even when, it's down or out for service. But in the DMV, with the mind for space and efficiency and sustainability, we typically, when a hybrid system is needed, put as small of a supplemental heat rejection or heat adder as you would need. These are great because what you'll commonly run into in urban settings is we can do almost all of it. We have enough for 70% of our load, but we just don't have enough for all of it. So this is where hybrid geothermal systems really shine. You can put in the space, as many wells as you have space for, optimize to the appropriate depth to maximize the benefit for your specific load. If it's really heating dominated, you go deeper so you can tap into that earth warmth. If it's cooling dominated, you go a little bit shallower so you can take advantage of the cooling effect that you get in the wintertime from the air. But either way, when you're constrained by space and you can't quite meet your load, these hybrid systems like are a great option for cashing in on a lot of the benefit. So like I said, one of the most common places is urban settings. So, while when you can't balance your loads in an urban setting, for example, you're facing DC BEPS, right? Like you're a building owner, you've been benchmarking your buildings and you've been told now that you face a penalty because your building is really inefficient. And you attended some webinars, have been reading the news, listened to the radio, and you've heard about these geothermal systems and you want to figure out, how to do it. So ultimately, in your case, where it isn't really feasible for you, you have an older building, it isn't feasible for you to maybe completely retrofit your envelope and air seal the whole thing and do all this other stuff to it. But if you are looking to upgrade your HVAC system, you could employ a hybrid geothermal system, which minimizes the lifetime and annual energy use, right? So at a certain point, if you put in just the boiler or have just let's say a gas-fired boiler, it's going to cost you a certain amount to operate. If you have the geothermal system, it's going to be cheaper, right? You kind of try to balance it so that you put in as much geothermal as that makes sense, so that you balance your first costs and you balance your energy costs on a life cycle basis over the entire life cycle of the system. So typically, successful strategies also are designs that have low thermal resistance boreholes and low pressure drop circuits, right? So you don't have to pump energy too hard to push it through the borehole. And when the water is in the borehole, it's able to pull a lot of heat out of the ground or reject a lot of heat back into the ground. Those two things, being really thermally conductive, like not very thermally resistant, and being pretty easy to move water through, those are really key for boreholes anywhere, but especially those in urban settings. And it's really important also in in all geothermals, but especially in urban settings where it's going to be harder. Like your geothermal system might be under your building or like under a parking lot or something where it's going to be a huge pain, as opposed to in a huge field, like a large open grassy field. It's really important that you employ inspections, commissioning, really a little bit of extra oomph, ideally via third party, to quality controlling your installation, so that the as-built condition really truly does match the design intent. I want to talk a little bit about a project that we worked on pretty recently. I think maybe 2019, 2020, we were out there on this in Wheaton, up in Maryland. It's a 14-story Class A, about a 300,000 square foot government office building. So this, again, trying to be energy efficient, but didn't have a lot of space. It's right kind of downtown in a built-up area. So it ended up using a hybrid geo exchange system with about 150 bores installed directly beneath the building. And since that quite couldn't cover all the needs, there was a hybrid. There was additionally some backup heat addition and backup fluid cooling. Still, on an energy basis, we were able to obtain energy efficiency almost 80%, as we would have if we were able to deploy an entire geothermal system without that supplemental heat addition and rejection. So again, showing even when we were constrained, we were able to work with the constraints and still leverage the geothermal to maximize sustainability. So this was a big team of folks. It was the Montgomery County Department of Transportation was the owner. O'Connell and Lawrence were their on-site consultant for construction management. Stonebridge was the developer they worked with. The management company, sorry, the Bazzuto was the developer. Gensler was the architect. GHT was the MEP engineer. Bowler was the civil engineer. Clark was the contractor. And we were specifically the geothermal commissioning agent for this. So we were there kind of providing review from the concept through the execution, through the testing, all the way at the end. So a few things about the building. This building is a bathtub design, right? So for those of you who don't know what that is it's basically the foundation is built like a bathtub, right? It's completely watertight. There may be groundwater, but the building floats, like it literally like floats like a boat, like in the water. Some of these buildings, I heard anecdotally at the site, they had to go through the wall for some reason. There was so much groundwater pressure that it was like a fire hose coming in, right? So no sump pump, you just keep the water out. You basically are building your building on a boat that floats on the groundwater. So it's All that to say that if you're going to put in vertical boreholes underneath a building like this, like you better be damn sure that they're not going to leak and that everything is going to work, because there is no chance, no opportunity to fix it. I believe the detail on top of this, on top of the bore field, shows that there is 18 inches of dirt, 36 inches of gravel, and then a net of 36 inches of concrete over these boreholes, right? So literally, we're not getting at them if something is leaking. So it was super, super important that we made sure that their design process was adequately done, that there were, all the checks and tests and inspections necessary in the construction phase were included, in the construction documents and contract documents, and then really made sure that it was built right. So a really interesting thing. One of the reasons that people don't like going under buildings, right, is because they're like, oh, what? Like, we have to dig out our foundation, and then you want me to wait for how long to drill 150 wells, right? 3, 4, 5 weeks? Like, are you kidding me? Like, I don't know. People often jettison geothermal for that reason alone, right? Because especially when it's under a building because it causes project delays. So there is a Canadian technique, which is pretty common now in Canada and is starting to become more common here, which we did here, which is you drill from grade, right? Like if you know that your foundation is going down 80 feet and that you need 400 feet boreholes, just start at grade. Like while you're doing permits and all that other stuff, you literally just dig a hole 480 feet deep, right? You drop the tube, you cut it and cap it at depth, seal off the tube, and then you continue your excavation for your foundation. And as you dig out and develop your foundation, eventually you arrive, at the tubes that you already previously bored, cut, capped, and sealed, and now you can proceed with your construction. So this is like a pretty clever way of doing boreholes like underneath a building, but not have minimizing the impact to your schedule. So super, super beneficial. Work well here. You have to be really careful though, right? So again, doing this type of thing creates more risk of scratches. Like I told you, there was a 10% limit. There's this slow crack growth that happens if it gets. So it's really important that there's testing and inspection protocols. Again, they're in the IGBA specification. I think CSA 448 was the Canadian spec that they adopted. Don't quote me on that, but you can find it on the IGBA website. It's really important that those procedures are followed, so that things can work. Like I can give an example here. One of the tests that's required is a hydrostatic pressure test, right? So after you dig all the holes, put all your pipes, hook them up, before you do anything else, you fill them up with water, pressurize it to 100 psi, you hold it for a while, you make sure you don't lose anything, right? If you lose anything, that means you're leaking. So on this project, right, the contractor kept doing it, the driller or the mechanical contractor, and they were like, we keep losing it, we keep failing this test. And they ultimately weren't reading the spec, right? The spec actually requires that you pull it up to 100 psi, and then since HDPE flexes a little bit, right? That's why I use plastic underground, so it's a little bit flexible. It resists earthquakes and other things that metal pipes are susceptible to, but it has a bit of flex. So when you put it up to 100 psi, it's gonna flex out a little bit, and you have to add a little bit more water to account for that. So they were seeing the flex and thinking, "Oh my gosh, there's a leak," and they did it 4 or 5 times before we were like, you really have to read the spec. And once they did it and kind of added a little bit more water and like maintained it, then they were able to actually comply. So there was no leak. They just weren't accounting for, you know, the letter of the law and how that test is written. So it's super important that it's specified properly. It has a default spec for backfill and inspections, and we, strongly recommend that you always do those. Okay, so that project was, a success. The Geo Exchange works really well. Really highlighted the importance of testing and inspection along with the design process. But when well executed, these systems are, phenomenal for energy efficiency. Um, you know, we talked about installing boreholes beneath buildings. One thing that's a new novel development is installing boreholes beneath existing structures, right? So there are actually new technologies. I think some of these are Swedish, but we see them proliferating, where they have these low height drills that can actually drill in existing slabs into the ground, with ceiling heights as low as 8 foot. right? So you can really do this in existing buildings. This is now slowly becoming a more viable option for commercial retrofit, even in urban settings. DC now does permit underground, boreholes under buildings and in existing structures. There's limits again as to how close they can be to the property line, but this is possible. And when people tell you it's not feasible, the building already exists, that's not true. These technologies are out there, and people are going these places. Of course, just like when you dig beneath the building, just like when you dig outside, there's call before you dig. You have to coordinate whatever underground utilities, subways, maybe sometime that are down there. But as long as you're coordinated, you can go down beneath the building, in an existing building, in a new building, or just as well as you can out in the green field. Couple of more ideas that are out there, getting a little bit more exotic and broadening up the conversation and broadening your opinion on what might be considered geothermal. We already talked about how you can go in the ground, or you can go in a body of water, like a river or a pond. But slightly more disgusting, people are realizing that the sewers are always kind of the same temperature, 50, 60 degrees. Even more disgusting, septic tanks kind of near your house or an individual building are kind of warmer, usually closer to human body temperature for obvious reasons. So these are a great source for heating and cooling. So these are called sewer exchange systems. So the DC water system uses these extensively throughout their water management buildings. The American Geophysical Union literally takes it out of a sewer main. There are off-the-shelf products. I think there's one called Shark heat pump that's literally designed for this. It's a big tank and a heat pump and a sludge, kind of a solids pump like you would see in a sewage ejector system. And they're basically heat pumps designed to use your sewage pit, right? Like as a tap the thermal energy from there. So when you can't quite make all of your load with the ground, this is another option. Maybe you don't need a cooling tower or a boiler if you can tap into your sewage pit. So wastewater coupled systems are increasingly common. Long time ago, mostly at like a municipal scale, but increasingly we are seeing these in schools, in community centers, and projects that are targeting net zero that already have ground source heat systems, geothermal deep vertical boreholes. They also include these to kind of help it along. That brings me to another picture that only an engineer could love, courtesy of the Gray Edge Group. Really a beautiful image if you're a mechanical engineer, probably horrible if you're anybody else. But it really, the point of this is it shows that anything can be used as a heat or a heat source or a heat sink with heat pumps. Over off on the right, you see these 8 little white boxes. These are kind of heat pumps, right, that are expecting, neutral temperature water, like we've discussed, either from a boiler and a cooling tower or from a geothermal system. But really, they can maintain their balance by taking in heat or cooling from a variety of sources. For example, not just you could connect it to this, closed loop earth heat exchanger. You could also attach it to an open source heat exchanger like a groundwater well or an aquifer or a pond. Or let's say you have a generator, right? And you use the radiator cooling water off of that, combined heat and power. For cooling, let's say your ground loop isn't enough, maybe you add a cooling tower or a fluid cooler. If your heating isn't enough, maybe you add a boiler. Maybe you add thermal storage, you just charge it overnight, get a little bit of, maybe you don't have quite enough for all of your boreholes, but you have some space above ground where you could put a phase change material. Maybe you have solar thermal, right? Like where you use the sun to recharge this temperature loop. Really anything can be used to work with a heat pump. The ground is free, but if the ground isn't quite available, there are lots of different sources for you to use to maintain that heat source and that heat sink, not just cooling towers and not just boilers, but tons of other ambient options, ranging from ponds to aquifers to even air source heat pumps or chillers when you want to do it a little bit more efficiently. There are tons of ways, and it's even when you can't go all ground source. Yeah, we encourage you to think of what other ambient sources of heat and cooling can you access to make your building more energy efficient. I'm going to stop there and switch gear and talk a little bit about the finance side of this, because this is expensive. But before we get away from the technical subjects, anybody have any questions? Okay. All right. Well, we'll have a few minutes at the end to take some more questions as needed. So one of the things that people point out, or rightfully say, when they talk about geothermal systems, yeah, if you're Sustainability hound, you might be finding a way of making it happen. But if you're a developer or somebody who's concerned with regulatory compliance and isn't really all about the environment, the first thing they're going to notice about this, aside from the time and coordination and design complexities, is that it costs a lot of money, right? These wells cost like $15,000 per well, a little bit less in cheaper markets, but in the DMV, that's what it costs. And where you might have a boiler and a cooling tower that together cost you 200K, now we might be talking about a bore field that costs 750K, right? It's a big cost add to do this. So how to pay for this, right? So there are incentives to help with this. So qualification, I'm an engineer, I'm not an accountant or a tax professional or anything else like that. So there are incentive tax professionals that specialize in this that can help. But basically, there is a tax incentive called Section 48 of the IRA. It also works for homeowners, Section 45L under the IRS tax code. It is the business incentive tax credit, the ITC, or the residential incentive tax credit. So we're going to focus on the commercial one here, just because that's mostly where these systems are used. The base credit is 6% of your qualified investments, right? So that can include the bore fields, the pipes, the heat pump, the distribution, really everything that's associated with the geothermal. You get 6% of that back no matter what. So if you meet prevailing wage and apprenticeship requirements, basically hire union labor, that incentive is increased 5 times. So it's 30% off of your first associated costs, and that's back as a tax credit. So even if you don't have liability, you can claim it. This is even available to like municipal governments and nonprofits, right? So even if you're like a non-tax paying entity, you can still take advantage of this credit, to make it happen. So you get even more. You can get up to 40%, additional 10% if you use domestic content. You can get additional 10% if you are in a energy community, which is so dictated by the government. I think there's even another few percent on there if you're like in an economically disadvantaged community. So you can end up getting 60% off, of your geothermal system associated installation costs back as a tax credit, to you within 1 calendar year of completing the work. So that's really huge. Even more beneficial, not everybody can take advantage of this, but for those that can, is typically HVAC and MEP equipment that when you buy it, you can depreciate it a little bit every year and write that off as a business loss. Typically, it's 27 and a half to 39 years, depending upon what the equipment is. But under the law, you can depreciate geothermal systems over 5 years. That means every year you can basically say it's losing 1/5 of its value and write that off as a business loss. So if you spend $1 million on your geothermal system in the right place, you can get 60% of that first cost back as an incentive, and then write off 1/5 of the actual non-incentivized costs as a business loss every year. So we find that the payback for these systems is often just a few years for a lot of folks that can take advantage of most of these incentives. I'll point out for those interested that these incentives actually have their origination in the George Bush years, right? 2005, the Energy Policy Act, I believe it was called. That time, for those of you old enough to remember, gas was pretty expensive. There was a war going on, and there was a lot of consideration about energy security. How does America become energy secure? So these incentives, right, for geothermal, renewable energy, energy efficiency are actually rooted in a desire for the country to be energy independent, for the grid to be resilient, so that everybody can get what they want when they ask for it and really meet our needs. So this isn't, while of course this is great, it's about sustainability, energy efficiency, the foundation of these incentives goes way beyond that. So for people talking to you about, hey, I don't care about this green, that green, why do I need a geothermal system? Like, what benefit is there? What does it do? Appeal to their sense of patriotism, appeal to their sense of, reliability, of getting of their, do I get what I want when I want it? There's way more to these systems beyond just beyond sustainability. Just to wrap up with an example of the tax benefits here, right? Let's say your geothermal HVAC cost is $1.5 million for your building and you have a tax rate of 21%, right? Off the bat, 30% tax credit, right? Let's say you use you've got union labor, 10% domestic credit, you buy all American equipment. Let's say you're in an energy community, already in year one, right? That's year one that you're getting as a tax credit. is 50% of the cost of your system, $750,000. So the ultimately the value of it after the tax shown there. Then each year you get to claim that depreciation over time. So ultimately, your total tax incentive not only is seen in the first year, but stacks over time. So even though for this project here, not ultimately over the life of the system, they were able to achieve a 61% savings rate. So the critical thing when you're talking about these in projects, whether they're existing buildings, your own property, a new development property, isn't to just get, look at the price tag and, have your eyes pop out of your head. It's, sure, this geothermal system, HVAC system costs 1.5 million, but what was a regular system going to cost, right? Like that was still going to cost money. Maybe that might have only been, half of it, $750,000. But, what if I get 61% of this back, in the form of cash over the course of the first 6 years of operation? It's actually cheaper to do geothermal once you draw the picture. So it's really important when evaluating these systems that you do a comparative analysis and just look at the gap between them so that you can really take these incentives and their effect into account. And remember, they don't only benefit you and your sustainability goals, but they do more to promote a resilient grid, an energy security for our country, and a whole host of other benefits, along with performance, maintenance, and energy efficiency and environmental benefits. So thank you all for sticking with me. That was a little bit longer than I had planned, but that's all I had today. So I'm going to stop here and see if there's any questions before we end today. I believe we have another 15 minutes. Okay. Well, thank you for joining. I appreciate all of your time. If you have any questions, again, my name is Ajit Naik, Baumann Consulting. Feel free to reach out to us. We'd be happy to discuss these technologies, systems, their design, construction, and operation more with you. We appreciate it. Thank you. Mark, anything else on your end before we end? Okay, guess not. Thank you all. Bye-bye.